In this lesson, we will get into decision trees, our first classification model. We will explore how decision tree works, the decision tree induction process, handling continuous valued attributes, and the pros and cons of decision trees. A decision tree is a tree-like data structure where each node represents a feature and each branch represents a decision and each leaf represents a class label. Key advantages of decision trees: they are easy to interpret even for non-experts. They can handle both categorical and continuous variables. So basically, continuous features will be converted to categorical features or ordinal features, so we can present them in this structure. And they use a recursive divide and conquer approach to split data into small subsets. In this classification stretch, we will go back and forth between two examples. In the play golf dataset, we want to predict if a person will go golf based on outlook, temperature, humidity, and windy. Let's pay attention at the class label column or play golf. So it looks like every time the outlook is overcast, the label is yes. But if the outlook is rainy, then it's going to depend on the humidity. When the humidity is normal, the class label is yes, but when the humidity is high, the class label is no. The second dataset is a real-world example about deciding whether to wait for a table in a restaurant based on multiple factors, such as, is there an alternative restaurant nearby? Is there a bar area to wait in? What's the price? How many patrons are there? And so on. Here you can find feature names and definitions. Let's take a moment and try to digest the decision tree. The key idea is that the tree evaluates one feature at a time until it arrives to a final decision or a class label. The patrons feature can take three values: none, some, or full. Based on the data, it's going to make its first decision. So if it's none false, some true, but full, then we need more information. One question we may start to think about: why does this decision tree start with patrons and not something else? And the answer: this relates to feature importance, which is going to influence the sequence in which features are going to be evaluated. We will learn several methods to compute this importance. Another observation is that we need to find a way to handle numerical data. In this very specific example, we were able to convert the weight estimate in minutes into discrete intervals and present them in the tree. But maybe in other scenarios, we need to perform some appropriate preprocessing. To sum up everything we discussed until this point, the big goal in decision tree construction is to find a small tree that is consistent with the examples. In other words, at any given level, we have a set of training examples, and we must decide which attribute will provide the best split. In this example, do you think patterns or type is a better splitting attribute? To answer the question correctly, we need to analyze the example. As you can see, there are 12 training examples. In 6 cases, the customer stayed in green, and in 6 cases, the customer left. Now, let's examine the values of patterns. For none, Every time there were no patrons, the customer left. For some, there are 4 cases when the customer stayed. But when patrons is equal to full, there were some times where the customer stayed and the customer left. So as you can see, there seemed to be a meaningful separation between the groups. On the other hand, the type of restaurant attribute, which has the values of French, Italian, Thai, or burger, doesn't seem to be splitting the examples into meaningful groups. So it seems that for each type of restaurant, customers stayed half of the time and left half of the time. That's why we're looking for those attributes that separates the data into meaningful groups. Now we get to a high-level description of the decision tree induction algorithm, which is basically a top-down divide and conquer approach. So at the beginning, we are going to identify the node or the attribute which will have a good split. And starting from this node is going to have all of the training examples available, and it's going to split the examples based on this attribute values. At subsequent steps on each node, the attribute selection is going to be determined by the remaining examples when we reach that node. So first we split based on patterns, then our statistical measure like information gain or Gini index is stated that we need to look into weight estimate. Then the remaining examples are going to be split based on the weight estimate and so on. More comments on this algorithm. This is a greedy approach, meaning we build the tree one step at a time. And by no means our goal is not finding the most efficient or smallest tree, because this is going to be expensive. Instead, we are trying to find a good enough tree in a feasible manner. So this is a computationally efficient algorithm, and the process can be parallelized, and decision trees in general are very interpretable, and we can debug and understand how the decisions were made. How to handle continuous valued attributes? Many datasets have continuous features like age, temperature, salary. One approach is called discretization, which means converting a continuous range into categories. In this example, we have age. We created the groups less than 20, 20 to 30, 30 to 40, and so on. Another approach is to find the best split points. Let's say we have a set of numeric values, so we go and sort them and try to find middle points between 2 consecutive data points. And then we are trying to use these middle points to identify which split is going to result in a maximum information gain. The split points which have a greater information gain are good candidates to split the values. Then we can have discrete categories like greater than P, less than P, and so on. Decision trees offer several advantages. On the top of the list, they are easy to understand and interpret. All what we need to do is to traverse the tree to understand how the decision was made. They are easy to implement and efficient, can tolerate some data quality issues, no normalization needed. But one important feature is they are non-parametric, which means this model does not make any assumption on the data distribution or if there is an independence relationship between the values. It can work on various attribute types, as we see. One major drawback of decision trees is their instability. They are highly sensitive to small changes in the data. Let's study this example. We have this two-dimensional data set with two features, x1 and x2. It seems that the decision tree first split the space based on the value 0.6, then subsequent splits managed to classify the data into region 1 and region 2. So region 1, the black data points, and region 2, the red data points. And everything looks very great so far. Now, suppose that we slightly changed the location of just one data point. We pushed it further down. You can see how the structure of the decision tree has drastically changed. So this is the big drawback in decision trees. Small changes in the data points is going to result in different tree structures, which means this is going to give us different classification results. It's not stable at all. More drawbacks: the accuracy may not be great because depending on the data and the structure of the decision tree that we got, it's very hard to find the most optimal tree structure. That's why we use greedy algorithms. And of course, there is the risk of overfitting, which means memorizing the examples inside the training data sets. And when something new comes up, it's going to be misclassified because this classifier was super tailored towards the training data set that they have at the time. Let's take a look at this graphic. It's a helpful way to visualize how dataset is split at each point. Initially, the data is divided based on the first selected feature. Then each subset is further split based on another feature. This process is going to continue recursively, refining the decision boundaries. In summary, we discussed decision trees, what they are and why they're useful, how they are constructed, and the recursive nature of the induction algorithm, techniques for handling continuous attributes, and finally, the pros and cons of decision trees.